Open a periodic table, and it looks finished. 118 elements, each in its own box, arranged into neat rows and columns, a structure so tidy it feels like a solved problem. Hydrogen up in the corner, the noble gases lined up along the right edge, everything falling into place the way a filing cabinet does. But that tidiness is deceptive. Every element in that grid is built from atoms. Atoms are built from nuclei and electrons. Nuclei are built from protons and neutrons, and even a single proton, the simplest possible nucleus, turns out to be far stranger than a labeled box in a chart. To understand why the periodic table looks the way it does, and where the tidy picture starts to break down, we have to go all the way down, past the atom, to the particles that build it. Take the proton, the particle every hydrogen atom is built around, and one ingredient in every other nucleus besides. The textbook picture is simple: 3 quarks, 2 up and 1 down, sitting inside the proton like 3 marbles in a bag. Each quark carries a third of the proton's baryon number, the quantity that makes it count as one whole particle rather than a fragment, and 3/3 add up to 1. It's a clean, even split, easy to draw and easy to teach. But that picture was always known to be incomplete. It glosses over what actually holds the 3 quarks together: a shifting web of gluons, the carriers of the strong nuclear force, binding everything into a single object. New data changes the story. Measurements from the STAR experiment at the Relativistic Heavy Ion Collider, published in 2026, favor an alternative picture, one where baryon number isn't split evenly across the 3 quarks at all. Instead, it's tied to the gluon junction, the Y-shaped structure where the lines of the strong force meet and connect the 3 quarks together. On this picture, what makes a proton, rather than just 3 quarks passing near each other, lives partly in that junction, not carried by the quarks alone. Even the most basic building block behind all of chemistry is still an open question in particle physics. That proton doesn't exist in isolation, it's one link in a much longer chain. Start at the bottom: quarks and gluons, bound by the strong force into composite particles called hadrons. Protons are one example, but not the only one. Bind gluons together, without needing any quarks at all, and, in principle, you get something called a glue ball, a particle made purely of the strong force binding itself into a lump. For 50 years, physicists have searched for clear evidence that glue balls actually exist. In 2026, the BESIII experiment reported its strongest evidence yet: a particle called X2370, whose properties point toward a gluon-dominated bound state rather than an ordinary quark-based one. That's one rung on the ladder. Bind hadrons like protons and neutrons together, and you get atomic nuclei, bound by a different residual version of the same strong force. Bind nuclei to electrons, and you get atoms held together now by the electromagnetic force instead. And bind atoms to each other, and you get molecules, the chemistry that builds everything from water to DNA. Quarks and gluons, hadrons, nuclei, atoms, molecules. Each step up is a new kind of bound state, governed by its own emergent rules, even though every one of them is built, ultimately, from the same handful of particles underneath. So why does the periodic table look so orderly, with its neat rows and columns going all the way up to element 118? It's tempting to assume that order has to stop somewhere, that eventually, physics simply runs out of new elements to make. But element 118 is where we've gotten to experimentally, not where the underlying physics says it must end. Follow the atomic number up the table, and quantum electrodynamics predicts something specific happens around a critical charge. Roughly Z equals 172 to 173. Past that point, the innermost electron orbital, the 1s level, is pulled down so strongly that it dives into the negative energy continuum. The ordinary atomic picture is expected to give way to a supercritical regime, where relativistic QED effects become dominant, and, in theory, the vacuum can become unstable against spontaneous electron-positron pair production. It's a real predicted transition, though one that hasn't yet been directly confirmed experimentally, waiting past the edge of the elements we've actually managed to synthesize. The periodic table looks finished at 118 only because that's as far as our tools have reached so far. not because the physics runs out there. Even before you reach that electrodynamic wall, there's a second one: nuclear instability. Most superheavy nuclei don't stick around long enough to do any chemistry at all. They fall apart in a tiny fraction of a second, decaying away almost as soon as they're formed. That's part of why the table thins out as it climbs. Heavier nuclei are, in general, less and less stable. But not all of them. Nuclear theory predicts an island of stability, a region of proton and neutron numbers where, instead of decaying instantly, certain superheavy nuclei might last dramatically longer, maybe even long enough to study in real detail. Reaching that island is an active experimental goal. As of June 2026, the Joint Institute for Nuclear Research is working toward creating element 119, using a reaction between berkelium-249 and titanium-50 nuclei. Whether that reaction succeeds, and whether the resulting nucleus lands anywhere near that predicted island, is a question for nuclear and particle physics to answer, not chemistry. The periodic table's next row, if there is one, will be decided in an accelerator, one collision at a time. Even within the elements we already have, the simple rules taught in introductory chemistry don't always hold. Take the transition metals in the middle of the table. The standard filling rule, the Aufbau principle, predicts that chromium should have the electron configuration argon, 3d4, 4s 2. But measured chromium actually has 3d5, 4s 1, one electron has moved from the 4s orbital into the d subshell. Copper shows the same pattern. The simple rule predicts 3d9, 4s 2, but the real configuration is 3d10, 4s 1. This isn't an isolated quirk, it's a deeper, deterministic effect that the simplified Aufbau rule doesn't capture. Half-filled and fully filled d subshells can gain additional stability from exchange effects, a quantum mechanical consequence of how electrons with parallel spins occupy different orbitals. When that stabilization is large enough, it contributes to shifting the balance away from the simple orbital filling order. Electron-electron interactions and orbital energy competition, including exchange and electron correlation, determine the actual ground state configuration. Relativistic effects matter too, but become increasingly important in much heavier elements. Quarks, hadrons, nuclei, atoms, molecules. Chemistry sits on top of all of it, but it isn't a closed system, sealed off with its own self-contained rules. It's one link in a much longer chain, resting on physics that reaches all the way down to quarks and gluons and reaching back up into every compound ever made. And once you stop treating chemistry as complete in its own right, its unsolved features start to look different. The gap at element 118 isn't necessarily the end of the table. It might just be where our current tools stop. The transition metal exceptions aren't stray anomalies. They're where a deeper rule was showing through the simplified one all along. So maybe finished was never really the right word for the periodic table. Perhaps it just depends on which rung of the ladder you happen to be standing on when you ask the question.